Hello.
Hello.
Hi, Rohi. Maybe we can give it a start and let others join in. Okay. I hope you can see my screen. So until yesterday, we are just starting off with defining the terminology. We defined a few other terminologies as well, and we are primarily going to look into regression. Hence, we'll start with simple linear regression, and then later on, once simple linear regression is completely understood along with the parameters, then we'll move on to the multiple linear regression. Okay, so let's start with the next set of things. So first of all, we have defined a few variables or a few names, and the names that we have defined is M is what we are calling the number of training examples which I have. X is the set of input variables or the features or the independent variables, right? So I've just used one more terminology right now, that is features. So independent or input variables are also known as features, while output variables or the dependent variables are also known as targets. Okay, so x's are the features and y's are the targets. Okay, so basis this, we were looking at some of the combinations of theta 0 and theta 1. If you remember yesterday, let me just draw. We were trying to draw the lines. Okay, if I draw it over here, it will not be good. So let me just draw it over here. So I'll just take the pen. Yeah, give me 1 minute. This is just to recap what we were doing yesterday so that we all are clear. So we took three
I'm
scenarios.
good.
Hi, Sarang. So we will take three scenarios, scenario one, scenario two, and scenario three. I'll just draw some random numbers here. So give me 1 minute. So let's say this is one a scenario with X having, let's say, three values, 1, 2, and 3, and Y having three values, 1, 2, and 3. Okay. And then we have our equation, which is H of theta inside brackets X, which is equal to theta 0 plus theta 1 x. Okay, so this is our equation that we have defined for a simple linear regression, where we have only one input variable or only one feature, and we are going to form this model which is basically going to approximate the value for y. So you can say y is equal to theta 0 plus theta 1 x as well. Right now we were looking at multiple combinations of what is going to happen. So for the rest two graphs as well, this is x and y, this is x and y. I hope you can see the drawing, right, clearly.
Yes.
Yeah, okay. So
Yes.
we have these x and y's, these three graphs, let's say, and we are going to take three combinations. Let's say this is something which we looked into yesterday as well, but I would just like to briefly remind you what we looked into. Let's theta 0 is equal to 1.5 and theta 1 is equal to 0. If this is the case, then in this case, you can see theta 1 being 0, this portion completely becomes 0, right? Then what is only left over to us is theta 0. So theta 0, as we have defined, is 1.5. If this is 1, this is 2, then approximately, let's say this is 1.5, then we are going to have a straight line, right? This straight line has a significance as well, okay? I will later come on and tell you, by almost by the end of this class, we will come to know that the straight line also has an importance to act as a very important metric when it comes to regression. Okay, but let's continue. Then again, imagine theta 0 is equal to 0 and theta 1 is equal to, let's say, 0.5. If theta 1 is equal to 0.5, then this part becomes x by 2 or 0.5 into x, and this part becomes 0, right? If this part becomes 0, then the line is something like this, a line that crosses the origin. And this line is so that it meets at a point. Is a very bad diagram, but I'll just try to make it up. So there seems to be a point on the line. There will always be a point on the line where for x value being equal to 2, the value of y will be equal to 1. Y, you can clearly see in this case, y will be equal to this value is not there. Theta 0 is equal to 0 and theta 1 is equal to 0.5. So it is x by 2, right? So y is equal to x by 2, which means for x is equal to 2, y is equal to 2 divided by 2 equal to 1. Hence, this will be the point 2, 1 from where the line is going to cross, right? Why is this equal to 0, or why this line is actually passing through the 0 barrier or the 0 point is because theta 0 being my intercept. This is what we defined theta 0 as yesterday. This is the intercept, and theta 1 is nothing but the slope. I'll also use a geometric function to define slope in some time. The slope is how slant this line is, and intercept is what is the initial value of y given the value of x being 0, right? So that is the significance of the interface and the slope. Now, for the third example, let's say this is 1, 2, and 3, and this is 1, 2, and 3 for x. So if theta 0 is equal to 1, and theta 1 is equal to, let's say, 0.5 again, then it will start from 1, and then it is going to take a shape like this, right? If that is the case, then my equation becomes what? Y is equal to 1 plus x divided by 2. So let's say x is equal to 2. If x is equal to 2, okay, then this becomes 1 plus 1, right? Or the answer is equal to 2. So there will be a point on the straight line which will be something like this. Okay, this point is going to represent 2, 2, right? For value of x is equal to 2, y is equal to 2 as well using this equation, right? So you can clearly see that this h of theta x being my model is actually defining the approximation of the value of y given there is a value of x, right? So that is what we learned yesterday. So let's try to continue from here. Now our question where we have stopped yesterday is that I need to find out, okay, I need to find out a way to ensure that I have the values of theta 0 and theta 1, and using that value, let's try to figure out how it is going to work or how I can formulate the equation. Now there are multiple ways in which I can do this. Okay, there is a concept of a cost function, but I will go to the cost function at a later stage. I'm going to simply try and define if there is only one variable. Okay, if there is only one variable, which is the case with us, we have only one x basis which we are trying to find out one y, then how can we figure out the value for theta 0 and theta 1? So for this, I'll get back to my notes again, and I'm going to write for a simple linear regression use case where we have one x and output of y, we can simply define the values of theta 0 and theta 1 as follows. Okay, so theta 0 is going to become is equal to, I can write theta 0, which in this case is the the equation is something like this: h of theta x, okay, is equal to theta 0 plus theta 1 x, right? And this is equal to y. So h of theta x is nothing but y. It is a model which is actually producing y. So theta 0 is the intercept and theta 1 is the slope. Okay, so keeping this in mind, what we can say, theta 0, and I'll write theta 1 as well over here. Theta 1 is the slope, okay, and slope is the correlation, okay, between X and Y. This is one of the factors which is going to define theta1, correlation between X and Y. We are also going to give it a name because we have seen how to calculate the correlation, right? Okay, multiplied by the standard deviation of Y, right? Divided by the standard deviation of X. Okay, now this is the general formula of finding out. I'll just put the brackets here so that at least we are able to understand what is going on over here. So numerator is this part and denominator is this part. Okay, the ones which are represented by the third brackets, you see. So in the numerator for theta1, we have correlation between X and Y. Now, if I want to find out correlation between X and Y, the techniques that I have already used are nothing but Pearson correlation, right? The calculations that we had done when we were learning statistics, right? So we have found out correlation between two random variables X and Y, and the formula is what is known as Pearson's correlation. Okay, so Pearson's correlation is an industry-wide standard. We can use it here as well. So Pearson's correlation between the random variables X and Y, we can find out, and we can find out the standard deviation of the data of Y, which is already provided part of the training set. We have the data Y. I can calculate the standard deviation of Y, and then I divide the entire thing by the standard deviation of X. I get theta1, right? So theta1 becomes my slope. Okay, so this is nothing but slope. Okay, theta0 is the intercept. Okay, the intercept is actually given as y bar, right? I'm going to write this as y bar because obviously in my keyboard I cannot type that y and a bar on the top. So y bar is the mean of y, or mean of the random variable y, minus slope times. Okay, so I'm going to use this slope times the mean of X. So this is X bar. Okay, even better will be if I put a bracket here, then it will be easier for you to understand. So I'll put a bracket over here as well. So first of all, I'm going to calculate theta1. I'll take the Pearson's correlation between X and Y. I take the standard deviation of Y, multiply this entire thing divided by the standard deviation of X, I get the slope. Then I calculate theta0, where theta0 is nothing but y bar minus this part, and this part is slope, which I've already calculated here, multiplied by X bar, where y bar is the mean of Y, X bar is the mean of X, and this gives me the intercept. Right, now there is a very clear problem in this. The very clear problem in this is what happens if I have multi-dimensional data. In this case, I have two-dimensional data. I have X and Y. It's very easy for me to visualize, right? It is easy for me to understand. It is easy for me to clearly see what is going on because I can clearly draw a scatter plot. It's very easy for me to draw a scatter plot, and because I have only two columns, it's very easy for me to do the calculations because I can clearly visualize it. Now, what happens when I'm going to have more than two dimensions? Then this theory will not work. If you clearly look at these two formulas, if you inspect them carefully, they are entirely dependent on the fact that I have X and Y. If I have X, Y, and Z, I can't no longer find the correlation coefficient between three variables. Pearson correlation coefficient works with only two random variables. It finds the relationship between two independent random variables, or the random variables might be dependent on each other, as we see in this case. That y, the value of y as we have presumed, which is nothing but the rent in the rupees, is actually dependent on x, which is the size of the house which I'm trying to rent in size per square feet, right? So that's why we call x as the independent variable, y as the dependent variable. A combination of these two random variables can be used to create the or to calculate the Pearson's correlation coefficient. What happens if there are more than two? I can't do this anymore, right? I cannot do this anymore. So I have to find out some other way. I have to figure out some other way to find out the values of theta0 and theta1. Now that way, and I'm going to write it over here, what we have we have defined above does not work beyond the scope of simple linear regression. Obviously, your real life choices will not be simple linear regression always. You can convert them into simple linear regression and try to do the regression analysis, but that is going to take a lot of time, right? So imagine if we have 30 columns, so 30 features or 30 independent variables and one dependent variable, you will have to create 30 different regression models or the regression lines, for each of which you have to calculate theta 0 and theta 1 and then come to a conclusion how to calculate the rent and so on and so forth basis that column. So that is really going to be very challenging for you. So that's why we need to find a better way of doing it. And that better way of doing it which is applicable to multidimensional as well as bidimensional data set is called cost function or cost function optimization. Okay, this is a very important kind of a topic and it is really difficult to understand at the first place. So what we are going to do is that we are going to find this out, but we will do this in a different way. Okay, first of all, we will look into what is the structure or what is a very generic method to create the regression line. And then we are going to get back or come back and look into cost function optimization, because if I directly jump to cost function optimization, we may not have the necessary mathematical background to understand this right now. Hence, I'm going back to the basics as to where or how that linear line or that regression line can be drawn. Okay, so let's go back and let's again try to draw something. So I have this x and y, okay, and I have some points. I have some points which are like this, okay. So I have some points which are like this. Okay, you can consider any example here. It is not really that important what use case you are considering, but let's say these are the points. So basis the scatter plot that I have drawn between x and y, this is what I get. If you want to guess what is going to be the worst regression line, okay, what is going to be the worst in the history of all the regression lines, the worst regression line will be something that passes through the mean value of y and which is actually a parallel line to x. Example, I just want to predict a very, very rough or loose approximation of what is going to be the value of y. I don't want to do all these scatter plots and all these theta 0, theta 1 kind of calculations and so on. Maybe I don't have the scope to do it. So I don't want to do all these things. I just want to do it as simply as possible. So irrespective of the size of the house, what I can simply do, I can simply take the average of y and I can say that the price or the rent that I need to pay in my city is the average of so and so. If that average is somewhere here, okay, I can simply draw a line which will look like this, right? This line is the worst regression line because I've simply taken the average of y and I've drawn a straight line. Why is this a straight line? Is because I now have an intercept which is the average, which is nothing but y bar. Okay, but I'm not considering any slope because at all I have not considered the value of x at all. Right, in this calculation that I've done, I've not considered the value of x. I've ignored completely the value of x and I've simply said no matter what the size of the house is in the city where I'm living, the average price, the average rent that I need to pay is as simple as you take the mean of all the rents and I'll get the average rent. So I can take that as a good approximation. Obviously, in real life, it is not going to work because you see what is the distribution of the data over here and how much this line is actually not fitting the data or how much this line is not really representative of this data. Now, how do we find why is this line not a representation of the data? Is the first metric that we are going to figure out. Okay, once we figure out the first metric, we will go ahead. Okay, to do that, let's make our life simple. And let's again draw the diagram with a very limited number of points so that we can try and see what is going on over here. So let's say these are the 4 points. Okay, I have only 4 points. Yeah, I have only 4 points. This is my y, this is my x. I hope the color choice is okay. And then I am selecting a straight line. I am selecting the red color. I'm saying this is the mean value. So irrespective of the value of x, I've drawn the regression line, which is just a straight line, which is parallel line to x. And this is the mean of y. So I simply write y bar here, right? Now, how do I say this line is how much good or how much bad? Is that I try to calculate what is the distance from this line to each and every actual point, right? So what I'm essentially trying to do is finding the distance or the value of y which is not matching with the predicted value of y or the estimated value of y. In other sense, I can call this y1, y2, y3, and y4. These are 4 actual values of y. And I can call these as y1 hat, y2 hat, y3 hat, and y4 hat. Okay. These values are actually the predicted values of y, right? Because I've simply taken the mean. Now, clearly, in this case, y1 hat or y2 hat, this nomenclature was not really required because all of these values are equal to y bar, right? Because this straight line is where all the values of y is equal to y bar, which is the mean. So how do I find the miscalculation in my estimation? This is the difference. So the difference for first point will be y1 minus y1 bar. For the second point, it will be y2 minus y2 bar. For the third point, it is y3 minus y3 bar. For the fourth point, it will be y4 minus y4 bar. I've ignored the signs. In this case, when I did the calculation, I did not see whether it is a positive point or a negative point. What is a positive point? Anything that is above the line is a positive point. I have to minus the mean or this y hat value from this value. And if it is anything beyond this, then I have to do the opposite. I have to subtract the actual value from the predicted value. Now comes a confusion. So to remove this kind of a confusion, what I do, I simply take each and every value of y, which is yi, and I minus the mean from each of the values. So this is yi minus y bar. I take a square of each of the value, okay, so that I can nullify the effect of plus and minus, and I take a sum of n or sorry, I is equal to 1 to m, where m is the number of the training examples that we have, right? M is my sample size. Yi is each and every actual value, and y bar is the mean value, right? So using this very basic and bad approximation of y, which is nothing but the mean, I get a straight line. Then I calculate the difference of actual versus predicted points, actual versus estimated point, actual versus estimated point, actual versus estimated point. I take a square. Why do I take a square? There is another reason behind it as well. If you have balanced data, then the positives are going to churn out the negatives. In other words, the sum of the positive values or the negative values is going to cancel out the sum of the negative or the positive values respectively. Hence, if you do a square, you get the absolute value. You take the absolute value, take a sum. Take a sum across all the points because you don't have a single point, right? You don't have only y1. You have y1, y2, y3, y4. So you take 4, right? You take 4 points and then you calculate this value. This becomes a good estimation, a somewhat good estimation as to how bad the model is. Okay, this is not how good the model is. We can't say how good is the model. Why? Because our y bar itself is a very bad thing to do. At the first place only we have done a very bad thing. We have taken the mean. This value, or this calculation is otherwise known as total sum of squared value or TSS. This is the first metric that we are going to discuss. The first metric, summation of I equal to 1 to m, yi minus y bar square, where yi is individual actual values, y bar is a mean of y, I equal to 1 to m is where m is the number of samples. I take a square, and this represents how much worse my model can become, how worse it can be, and that value is equal to TSS. Right? I hope this was clear. So I'll just take this line above, and I'm going to say one of the metrics to ascertain how bad or even good my model is simply to take the average of y ignoring the values of x at all, using x y bar, and then using y bar I draw the regression line. Right, I draw the regression line using y bar, then followed by the calculation of each actual versus expected or predicted or approximated value of y, taking a square of which to nullify the effect of positives and negatives, right, and also the scale. We can take a sum for all the values of y and call this output as total sum of squares, right? So this is what is the first metric which we have. Clearly, this metric is not going to tell me how good the model is. It is actually the opposite thing to say how bad the model is. Okay, but at least we have made a start. Now we would like to look into some other metric where this is not the case. So this will usually not be the case, right? That we are going to simply calculate y bar. If that is what we are going to do, then why are we really learning what the things related to predictive analytics, right? Let's clear this diagram. Let's again go back and try to take another example. This is y, this is x, and I have some points which is something like this. Now I take a straight line and I fit the regression line, which is something like this. Let's say this is one of the lines that I've chosen. Okay, I have chosen one line since we are 3 of us in this class. So we are going to choose 3 lines. Okay, I have chosen one line. I'm going to give this a name. Right, this is my line. The rest of the 2 lines I'm going to draw a little later because I need to explain something here. After I have explained, then I will draw the rest of the 2 lines. So for this first line, for each and every value of x, I have got the values of y, which is this. These are, sorry, let me choose a different color. These are the actual values of y. And for this is the predicted value of y. So again, I take the difference. Right? I follow the similar kind of procedure. I take the difference to ascertain how much this value is going to be. What is going to be the delta, or what is going to be the difference between actual and the predicted value. If I take a square of these now, then this line over here no longer being representative of y's mean, because this is y and this is x, and this line is definitely not y bar, because if it is y bar, it would have been a straight line. This line is kind of a regression line. We don't know whether it is a good line or a bad line, and that is exactly what we're trying to find here. But this line being my regression line, I have already written my name as well. I take the differences, which is of the actual value, which is yi minus y1 bar or y1 hat. Then I take y2 minus y2 hat. Then I take y3 minus y3 hat. And finally, I take y4 minus y4 hat. In this case, I can confidently do this because as opposed to the previous case, my y1 hat, y2 hat, y3 hat, and y4 hat is not equal to y bar. So I can do these kind of calculation. I can sum them up. And if I sum them up, I can write them up as sum of I is equal to 1 to m yi minus yi hat square. If I do a calculation like this, right, this terminology now, or this summation, is what is actually defining or helping me define how good this line is by calculating the errors in the estimation that I've done, the errors in the approximation that I've done. That's why this total is called SSR, where this value R, this is a very important terminology. This value R is the individual errors otherwise known as the residuals. Okay, these are the individual errors, the differences from each actual point versus the approximated point known as the residuals. I'm taking the sum of squares of all the residuals. That's why this SSR is known as sum of squares of residuals, right? So this is known as sum of squares of the residuals. So this is an approximation of how closely good my model is. Now let's try to clear everything. And again, we are going to draw our example because I've only drawn one line, right? We are 3 people in the session. I must draw 3 lines. Let's first of all draw the points. We will take red this time. And let's say these are my 4 points. Or this is too close to it. So let's say this is my 4 points. Now I'm going to take a line. This is my line. Okay. And I'm going to take the other line, or maybe I'm going to write my name first, right? Otherwise, I'm going to forget whose line is what. Then I'll take another line. I'll mark this into a different color. Okay. And I'm going to say this line actually belongs to, let's say, Saransh. Okay. And then I take the final line because we are 3 people. And I say this line belongs to Rohi. So we 3 have individually created the regression line. So this is my line. Okay. This one is my line. This one is Saransh's line. And this one is Rohi's line. How do I come to know? How do I come to know which line is actually a good line? Which line actually fits the situation better? In other words, which line gives me the best h of theta x? Because that line itself is going to determine what is going to be the value of theta 0 and theta y. Right? If I am able to calculate the best line, I can see what is the intersection. From the intersection, I can get the intercept. If I get the intercept, I can reverse engineer, get the slope. Or I can also calculate the slope by looking at the rate of change. So I'm going to use bits and pieces of also calculus in this, try and find out the slope. In other words, I can also find out the slope in some other way. I don't have to do any mathematics there. I just find the angle here. So let's say I'm concentrating only on the Rohi's line. And here this angle is, let's say, theta degree. I simply take this angle and take a tangent. Okay, tan of theta. If you remember basic geometry, you want to consider the slope of any line that's actually the tangent of the degree covered by that line. So in this case, it will be tan of this line, right? For my line, which is drawn in this blue, okay, this is my theta, right? If I take a tangent of this, right, I take a tangent of this line, I get what is the slope of my line. In the same way, I've already got what is the slope for Rohi's line. In the same way, I can get that for Saransh's line. So I can get θ1 and θ0, not a problem. But before I go in there, as I said earlier, I need to decide what is the best line. What do I do? If I want to get that information, what do I usually do is that, okay, I simply have to calculate the RSS value, right? The RSS value for each and every line. How do I do that? This, and this. So calculating the residuals for these 4 lines that I've drawn, this gives me the SSR for my line. In the same way, I calculate the SSR for Saransh's line. In the same way, I calculated the SSR for Rohi's line. Whichever SSR is the minimal is going to be the best for me. Why? Because in that line, the difference or the sum of the difference between actual and predicted is the lowest. Right? In this case, maybe we come to a conclusion that let's say that after all the calculations, we come to the fact that Rohi's line is actually the best line. Okay, if we consider Rohi's line is actually the best line, we are going to delete the rest of the assumptions. We are going to get rid of the rest of the lines. We are only going to concentrate on Rohi's line, find the tangent of this degree, and I get the slope, and I find the value of this. I get the intercept. So I get θ1, or I get θ0 from here and θ1 from here. I put that into the equation which I already have. Okay, the hypothesis equation AH of θx is equal to θ0 plus θ1 into x. I get my linear regression equation. Once I get the linear regression equation, I can clearly say that for any given value xg of x, I can estimate the value of y using h of θx. Right? So let me just clear the drawings and come back here. And I'll write, similar to TSS, RSS provides the idea about how good the regression line has fit the data. In this case, we must define R first. Okay, R, sorry, this should not be RSS, this is SSR. Okay, not RSS. So, or it can be called RSS as well. Residual sum of square is also what is called. And this TSS is also known as sum of squared of totals. Okay, so TSS can be called sum of square of totals as well, SST. And sum of squared of residuals can also be known as RSS, residual sum of square. R is called the coefficient of determination. This is a new language that we are introducing. Coefficient of determination, which helps in finding the variance between the actual data and the estimated data. Taking a squared sum of all the residuals will help figure out the scenario better by nullifying the scale, right? So we get the RSS, we get the TSS, we get the RSS. Now I'm going to introduce you to the last metric of the day, and then we can make it close. Why are we only going to be concerned with TSS or RSS or SST and SSR, howsoever you want to call it, and why not something else? Is there any problem with TSS and RSS? The problem comes when you have the model and you want to reuse the model. The final goal is always to get a model. Let's say h of theta x is my final model. Okay, I want to reuse this, so I put some data as an input. I must get the output. That's what we have declared yesterday as well. I give it unknowns of x, or given values of X, it gives me the unknowns of Y, right? If I have a data set, which I have already looked into earlier, where X is the X is the size of the houses, Y is the price. Size of the houses is given in square feet, right? Let's say the scale of that is 10 of square feet. And I have this data where Y, the price is in rupees of thousands, right? So basically what I say is a 700 square feet flat will be represented as 70 over here. 70 multiplied by 10 is going to be the actual value. And the price of that, or the rent of that house, let's say, is 10,000 rupees. So I write that as 10 over here because I multiply 10 to the scale, and then I get the actual value. So this is one way. This is one data set which I have, combination of X and Y. If let's say there is someone else who don't want to do all these confusions and complications and so on, he simply writes X and Y in the actual scales. Okay, I have 700 square feet of flat. My rent is 10,000. You see the degree, the scale is actually changing. If you do the calculations by hand after this session is over, the values of TSS and RSS is going to change. The values of TSS and RSS is going to change, irrespective of the fact that we have the same model getting applied on the same scenario. It is just dependent on the scale of the data that the values itself of TSS and RSS are changing. Then that is a problem. I don't have any reliability. How am I going to solve this? Right? How am I going to solve this is, I take 1 minus RSS by TSS and I call this the R squared value, where R squared falls in the range of 0 to 1 and it is a probabilistic value. Why is this a probabilistic value? Why it falls between 0 and 1? Something that is going to take at least 10 minutes of our time. We don't have that time right now. Let's make it a call, or let's make it a close now. I'll stop the sharing. We will be continuing tomorrow. Okay. Thank you so much.